Okay, our continuation from our previous video. We just finished talking about the difference between population distribution, distribution of sample data, and the distribution of a sampling distribution. Alright, so here's an example. A breakfast cereal includes marshmallow shapes in the following distribution. 10% are stars, 10% are moons, 20% are rockets, 40% are astronauts, and 20% are planets. We are interested in the proportion of rockets in a random sample of 2,000 marshmallows from the cereal. What we're going to do is we are going to sketch the population distribution of the marshmallow shape. So what would that look like here? Well, we would want to sketch out a bar graph. Not a histogram, but a bar graph, okay? And then for B, suppose you're to collect a random sample. Sketch distribution of the sample data you expect to see. Honestly, it's going to look basically identical to the population distribution. The only difference is that on your y-axis, instead of having the proportions, you're going to put how many out of 2,000. So if you expect 10% stars, the stars column would go up to, what is that, 200? And then for C, suppose you collected many samples of the same size, sketch the sampling distribution of the proportion of rockets you think you would see in the samples. Well, the population, there are 20% rockets, okay? So your distribution, you would think most of your samples would be about 20%, but you could have some more, some less, but it would basically be centered around 20%. So again, another histogram actually for that one would be better. Or you could do a dot plot. Okay, let's talk about bias and variability. And we're going to look at in class, guys, what this would truly look like. So if you're unsure what your graph should be, try the best based on what I've said, and then we'll go over it in class. Bias and variability. Bias means that our aim is off and we consistently miss the bullseye in the same direction. Okay? Our sample values do not center on the population value. Now, variability. High variability means that repeated shots are widely scattered on the target. Repeated samples do not give very similar results. So think of this as like target shooting. All right, and we have these 4 targets here. This top left one, high bias, low variability, meaning if this is where we want to hit center, we are off. But we're consistent as far as, you know, very similar results, but it's not the results that we want. So this is high bias but low variability. For B, low bias. So we are close to the bullseye, but high variability in that they're widely scattered on the target. C, high bias, high variability. This is awful. You're not even close to the bullseye, right? What you would expect, and then you're all over the place, not near where you want to be. This is the ideal one, right? You are hitting your target, the bullseye. You're close to the center of the population value, and it doesn't vary too much, right? We're kind of very close together as far as our values. When picking a statistic to use to estimate a parameter, we should use an unbiased estimator. Unbiased means it's not consistently too high or too low. Mean is generally unbiased. Now, biased, it has a pattern of being too high or too low. Range is generally biased. And this is assuming that the sampling process we are using has no bias. All right, so assuming that whatever we're doing to get the data, there's no bias there, that's what we're going with. So if we're looking here, if down here we see this is the true value of the population characteristic, which statistic is unbiased? There are actually 2 statistics, 2 and 3, because their center matches up with the true value of the population characteristic approximately. The difference between these two is the variability. Statistic 2 has lower variability than statistic 3. Statistic 3 is a wider spread of values, whereas statistic 2 is a less wide spread. Now, when you're describing your sampling distribution, you go through your SOCS. The center. A statistic used to estimate a parameter is an unbiased estimator, right? We said this is most accurate. If the mean of its sampling distribution is equal to the true value of the parameter being estimated. So important, okay? If the mean of the sampling distribution is equal to the true value, right? Think about the bullseye. You're hitting where you are expected to hit. The spread. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. Notice how it doesn't say it's determined by the size of the population. We don't care what the population size is. The spread is determined by the size of the sample. Okay? The spread of sampling distribution does not depend on the size of the population, as long as, this is important though, as long as the population is at least 10 times larger than the sample. This is that 10% condition that we have talked about before. So notice here, we're looking at a count of 1,000 samples, and here's our sample proportion. They both have the same center, but when my sample size is 100 versus when my sample size is 1,000, look at how reduced the variability is between these two. And then shape. Sampling distribution can take on many shapes. The same statistic can have sampling distribution with different shapes depending on the population distribution and also depending on the sample size. Okay, this is just showing sampling distributions for different statistics used to estimate the number of tanks in Germany during World War II. The blue line represents the true number of tanks. You can see here on the side, it's kind of hard to understand, but it's telling you where the data came from. So like if we doubled the mean, or if we had the max versus the min. If we want to reduce variability, which is something we would want to do, right? You would want to have low variability and no bias, ideally. In order to reduce your variability, you want to take a larger sample to get a smaller spread, okay? But the sample size does not depend on the population size as long as the population is at least 10 times bigger than the sample. Now, reduced variability doesn't eliminate bias, right? Look at this example here. There is very low variability, but still very biased. So, just because you have a larger sample doesn't mean it's not going to be biased. In the next two sections, when we learn about the formulas, you'll see how having a larger sample affects the formulas for calculating variability, right? So that'll help you see there. And that wraps up this video. We're going to do some practice with us in class. Look at the textbook sample problems that I've also written down at the bottom of your page, because they are going to definitely help you with doing the practice for this section. All right, have a good one.